What happens when you zoom in beyond the nucleus of the atom? If the nucleus is made up of only positive and neutral particles, what stops it from simply just falling apart? And what happens when matter and antimatter collide? To answer these questions, we need to understand what particles make up the matter we interact with every day by building up a family tree of particles from the ground up. Now, if we want to classify all the particles, we just start off with the ones we already know. If you've taken any science class at school, you've likely seen the Bohr model of the atom. Here we have an atom of helium-4 The proton has a charge of +1. The neutron is neutral. Both have roughly equal masses. The electron has a charge of -1, but is a much smaller mass, roughly 1800 times smaller than the proton. In 1964, two physicists, Murray Gell-Mann and George Zweig, both independently proposed that protons and neutrons themselves are not fundamental particles, meaning they're made up of other, smaller particles. Then, in 1968, physicists conducted experiments at the Stanford Linear Accelerator Center, where the team fired electrons at protons and saw how they bounced off. The scattering patterns produced by this experiment appeared to have come from smaller particles inside the protons. Then at CERN, scientists confirmed that these inner particles had fractional charges of 1/3 and 2/3. The particles observed were in fact quarks. The three most common quarks are the up quark, down quark and the strange quark, followed by three less common quarks, the charm, top and bottom quarks. Today, we'll only focus on the three most common quarks, the up, down and strange quarks. The up quark has a charge of 2/3. The down quark has a charge of -1/3. The strange quark also has a charge of -1/3, but unlike the up and down quarks, it has a strangeness of -1. Strangeness is a quantum number, an intrinsic property of a particle. You can think of it as kind of a particle's personality trait. Strange particles were found to have longer half-lives than expected, which is, well, strange. Strange particles were observed to always be produced in pairs, so we assign them this property called strangeness, which is conserved. Sometimes. Hadrons are a group of particles made up of quarks. The hadron family is split up into two groups of particles, baryons and mesons. Baryons are particles made up of three quarks, such as the proton and the neutron. The proton is made up of two up quarks and one down quark. Here, we see the charges add up to +1. The neutron is made up of one up quark and two down quarks, so the sum of their charges is 0, making the neutron neutral. Gell-Mann actually took the word for quark from a quote in James Joyce's novel, Finnegan's Wake. 3 quarks must a mark. As it was discovered that baryons are made up of 3 quarks, the quote was quite fitting, so the word stuck. The other group of hadrons are the mesons. These are comprised of a quark-antiquark pair. Yes, you heard that right. Antiquark. Let's briefly talk about antimatter. All particles have their own antimatter counterpart, having an identical mass, but the quantum number will have an opposite sign. Let's take an example, the electron, with a charge of -1. Its antimatter counterpart is the positron, which has an equal mass, but a charge of +1. Again, the proton has a charge of +1 with a quark configuration of up, up, down. The antiproton will therefore have a charge of -1 and configuration of anti-up, anti-up, anti-down. For a strange quark, the -1/3 charge and strangeness of -1 will be flipped for the anti-strange quark, a charge of +1/3 and a strangeness of +1. So, what happens when a particle and antiparticle collide? When a particle and its corresponding antiparticle collide, they annihilate, ceasing to exist. Let's look at an example here. An electron and a positron. The two particles are oppositely charged, so they attract each other, causing them to collide. When they collide, the particles cease to exist. Now, unless you've lived under a rock your whole life, you've likely heard of Einstein's mass equivalence equation, E = mc², meaning that mass is a form of energy, meaning if two particles cease to exist, energy cannot be created or destroyed, so energy has to be transferred into another form, light. So, if we go back to the animation, when our electron and positron collide, two photons, two particles of light, will be produced in opposite directions. Why 2? This is to conserve momentum. The pair of particles are coming together with the same speed, but in opposite directions, so the sum of their momenta is 0. Meaning, when the 2 photons are produced in opposite directions, the sum of their momenta is also 0. And yes, photons do carry momentum, even though they have no mass. It's very weird, but that's a topic we'll talk about in a later video because it's too much to explain now. So how much energy do these photons have? If we assume the electron and positron had 0 velocity before they collided, the sum of the energy of the 2 photons is equal to the sum of the rest masses of the electron-positron pair. Rest mass is simply the mass or energy of an object at rest. The rest mass of an electron is 9.11 times 10 to the minus 31 kilograms. So the sum of the pair's rest masses is 1.82 times 10 to the 30 kilograms. Using our E=mc² equation, we can find the total energy of the photons by the rest masses times the speed of light squared, which is 1.64 times 10 to the minus 13 joules. So each photon will have 8.20 times 10 to the minus 14 joules of energy. We can figure out what frequency of the light produced will be using Max Planck's equation, E=hf, where h is the Planck's constant. So the frequency is 1.24 times 10 to the 20 Hz. This means a gamma ray, the most intense radiation, will be produced by annihilation. The same interaction can happen in reverse as well. This is called pair production. If a photon had an energy greater than the mass of a particle and an antiparticle, the particle-antiparticle pair can be spontaneously produced. If this photon had an energy greater than the rest mass of an electron and positron, the photon can spontaneously convert into an electron and a positron. These again will move in opposite directions to conserve momentum. Any extra energy above their rest masses will be converted into additional kinetic energy in the particles. If discovering that pure energy can spontaneously create matter and antimatter from thin air just changed how you see the universe, subscribe to learn about more physics that governs everything from quantum particles to cosmic phenomena. Now that we've covered what antimatter is and how it can form, we can go back to the second group of our hadron family, the mesons. Mesons are made up of a quark-antiquark pair. Using our 3 most common quarks, the up, down and strange quarks, we can formulate a diagram of the most common mesons, pions and kaons. Pions are comprised of only up and down quarks, so at the centre of our diagram we'll have the pi-naught meson, either comprised of an up anti-up pair or a down anti-down pair. It's called the pi-naught meson as the quark configurations have charges that sum to 0, naught. The other pions are the pi plus meson, made up of an up anti-down configuration, and the pi minus meson, made of a down anti-up configuration. For our kaons, we'll add another 2 rows for these. Kaons are strange particles, meaning they contain a strange quark. Let's start with a k-naught meson. This is made from a down anti-strange quark pair, so it has 0 charge, but a strangeness of +1. Its corresponding antiparticle is then the anti-k-naught, with a strange anti-down quark pair. It still has the same charge, but the opposite strangeness. Then we have the K plus meson, made up of an up anti-strange configuration, and finally its antiparticle, the K minus meson, made up of a strange anti-down quark pair, finalizing our web of mesons. To summarize, hadrons are a group of particles made up of quarks, split up into 2 groups, baryons, made up of 3 quarks, and mesons, made up of a quark-antiquark pair. These particles interact with a strong nuclear force. The strong force is one of the 4 fundamental forces in physics: the gravitational force, the electromagnetic force, the strong nuclear force, and the weak nuclear force. What exactly is a strong force, you may ask? Well, you may have asked the question, why doesn't the nucleus simply just rip itself apart from all the positive protons repelling each other inside the nucleus? Well, there is another force at play, the strong nuclear force. This force is very different to gravity and electromagnetism. It acts an extremely small distance and varies peculiarly with distance. The scale of the force we're using will require a unit you likely have never heard of, the femtometer, equal to 10 to the minus 15 meters, roughly the size of a proton or neutron. To understand how the strong force works, let's draw a graph of how the force varies with distance. Any value above the x-axis will represent a repulsive force. Any value below the x-axis will represent an attractive force. We see from 0.5 femtometers onwards, we have an attractive force. This is the force that is holding the nucleus together from the repulsion of the electromagnetic force, and after 3 femtometers, we see that the strong force is effectively negligible. So this force only really acts within the nucleus. From 0 to 0.5 femtometers, we see the strong force is repulsive. This keeps the strong force from causing the nucleus to collapse in on itself. Now that we've understood what hadrons are and what the strong nuclear force is, we can now introduce the other branch of the family tree of particles. These particles are called leptons. Leptons are fundamental particles that do not interact with a strong nuclear force. There are 6 leptons, the first 3 being the electron, muon and tauon. Each of these particles have a charge of -1. Muons and taus are essentially heavier versions of the electron, about 200 and 3,500 times more massive respectively. Their higher masses make them more unstable, so they quickly decay down into electrons. This is why you don't see them in our atoms. The other 3 leptons are the neutrinos, the electron neutrino, muon neutrino and tau neutrino. Again, like the electron, the muon and tau neutrinos are heavier variants of the electron neutrino. Neutrinos are tiny neutral particles, which gives rise to their name in Italian, meaning little neutral one. The neutrino was proposed long before the quark, back in 1930 during experiments looking at beta decay. A classic example is the decay of carbon-14 to nitrogen-14, which is the basis for carbon dating. In this decay, a neutron turns into a proton and emitting an electron as a result. Scientists expected that the electron would carry away all the excess energy produced in this decay. Instead, when the experiment was conducted, the scientists observed a continuous distribution of kinetic energy of the electron, not a single sharp kinetic energy as they predicted. Something was missing. To explain this, in December 1930, Wolfgang Pauli wrote a letter to a conference in Tübingen proposing the existence of another particle produced in this beta decay, a light mass neutral particle. Pauli knew that for there to be a continuous distribution of energy, there must exist another particle that can carry off some of the energy that the electron would have. The total energy stays the same, but how it's split between the electron and the new particle varies from one decay to another. This is why the electron's kinetic energy appears as a smooth spread, not a single value. It took another 26 years after Pauli's proposal before they officially detected the neutrino. In the early 1950s, Friedrich Rhines and Clyde Cohen took on this challenge. They first built a 300 large liquid scintillator named Herr Auge, German for Mr. Eye, to catch a glimpse at these elusive particles. Nuclear reactors are ideal sources of electron antineutrinos, as nuclear fission produces many, so they placed the detector next to one. But their initial attempt failed. Cosmic rays constantly bombarded the detector, drowning out the neutrino signal. The two were undeterred by this, so they redesigned the detector to a 3-layer detector that could easily distinguish between neutrinos and background noise. After a year of careful data collection, they succeeded. In June 1956, a telegram was sent to Pauli with the triumphant words, "We're happy to inform you that we have definitively detected neutrinos." We've mapped out the fundamental particles that make up everyday matter, from the elusive neutrinos to the quarks that make up protons and neutrons. But this family tree is more than a list. It's a story of interactions, decays, and the hidden rules that govern everything we see. In the next video, we'll dive into those rules, the conservation laws, and the invisible messengers of the forces. Because to understand particles, we need to know how they talk to each other. My name's Kian Zanjani, thank you for watching.